Welcome back to the Deep Dive. Today, we are putting aside the hype cycles and the big flashy press releases.
We have to.
We're stripping this down to the metal. We're looking at what I can really only describe as a singularity moment for the entire automotive industry. Specifically, this window we're sitting in right now, 2024 to 2026.
It is a singularity. I think that's the right word. Because the rules of physics, or at least the rules of business physics, they're starting to break down.
How so?
Well, for the last, decade? We've heard the term software-defined vehicle, or SDV, just thrown around at every single conference.
It became the ultimate buzzword.
It absolutely did. But if you look at the stack of technical strategy reports we have on the desk today, and we're pulling from McKinsey, FEV, UL Solutions, SimScale, that era is already closing. We're crossing the threshold into something new.
Which is?
AI native architecture.
And that's a critical distinction, isn't it? Because SDV was, about updating your infotainment system or maybe tweaking the battery management system over the air.
Right. It was about software on the vehicle.
But AI native. This means probabilistic artificial intelligence is now defining the vehicle's core behavior, its entire development process, and crucially, its safety case.
Exactly. And if you are a CTO or a chief engineer at a major OEM right now, this transition, it isn't just interesting. I think for a lot of them, it's terrifying.
Why terrifying?
Because you're caught in a pincer movement, a classic strategic trap.
Okay, let's define that pincer, because this really sets the stage for our whole discussion. On one flank, you have what the reports call the need for speed.
Right. The market has just fundamentally shifted. It's being driven by the cadence of consumer electronics and, frankly, the aggressive iteration we're seeing come out of China.
So the old timelines are just gone.
Gone. We used to have 48, maybe 60 months to build a car from scratch. Now the market demands 12 to 18 months for a major refresh. It's a brutal compression.
But then you look at the other flank of the pincer and you hit the compliance wall.
A very, very thick wall. We are seeing the strictest safety regulations in the history of the automobile hitting exactly in this 2024 to 2026 window. The EU AI Act is now live.
And the big one, ISOPA's 8800.
The new Bible for AI safety. It's in effect. It's not a future problem. It's a today problem.
So it creates this impossible engineering paradox.
That's it. The C-suite is telling engineering, go twice as fast as you ever have, but be 10 times as safe as you've ever been.
You can't solve that equation with more headcount or, just working weekends.
No, you can only solve it with a completely new technology strategy, a fundamental rethink.
Which is exactly why we're formatting this deep dive differently today. We're going to treat this as a formal technology strategy report.
I like it, putting the consultant hat on.
We have to. The topic is just too complex for a casual chat. We're going to adopt a top-down and MECE that's mutually exclusive, collectively exhaustive approach.
Good. Structure is our friend here.
We have 5 specific sections to cover. First, the strategic landscape. Follow the capital, the geography, the speed. Second, the engineering revolution. Specifically, how AI is compressing the traditional V model.
The really technical stuff. Good.
Third, we'll look at the product architecture, the big shift to end-to-end autonomous systems and what that means. Fourth, the safety moat, a deep dissection of ISOPA's 8800.
The compliance wall itself.
Exactly. And finally, the implementation strategy, the actual playbook for survival. What do you do on Monday morning?
That is comprehensive roadmap. So let's start at the top, Section 1.
Section 1, the strategic landscape. And, you always have to start by following the money.
The capital allocation tells the whole story. It really does. If we look at the numbers, the global automotive AI market is valued at approximately $18.2 billion in 2025.
Which is already a huge number.
It is, but the projections for 2026, they jump that to over $21 billion. So depending on which analyst report you trust, you're looking at a compound annual growth rate of somewhere between 15 and 30%.
But the raw growth number, it almost masks the real story, doesn't it? It's not just growth. It's about the migration of value.
Correct. That's the McKinsey view right there. The hardware profit is evaporating. If your business is stamping metal, casting pistons, or assembling seats, your margins are being compressed to near zero.
The value is just gone.
It's shifting. The entire value pool is moving into software and AI services, and as a direct consequence, R&D budgets are fleeing the traditional mechanical engineering departments.
Where?
They're being reallocated to 2 main areas: AI compute, and what the reports are now calling data factories.
Okay, I want to drill down on that term, data factories, because it sounds like a buzzword,
Yeah.
but in this context, it implies a massive industrial infrastructure.
It is not a buzzword, it is an asset class. A data factory isn't just a server closet in the basement of the R&D center.
Right.
It's a dedicated industrial-scale pipeline for ingesting petabytes, literally petabytes of raw video data from your fleet, cleaning it, auto-labeling it, and using it to train these massive foundation models.
So the capital intensity has shifted.
Completely. It is as capital-intensive to build a data factory today as it was to build a stamping plant 30 years ago.
And this incredible capital intensity is driving a geopolitical fracture. The report we're looking at describes a splinter net of automotive tech.
A great term for it.
We don't have one single global market anymore. We have distinct and sometimes incompatible technology stacks based on geography.
Let's break them down because the strategies they're employing are radically different, and you need to understand all of them to compete.
Let's start with China. The reports classify the region as the data-driven radical.
The pace is it's blistering. There's no other word for it. They are leveraging a speed-first strategy.
Meaning
They prioritize iteration and deployment above all else. You look at a company like Huawei with their ADS 3.0 or Xiaomi with the new SU7, they are pushing end-to-end autonomous adoption faster than anyone else on the planet.
And they can do that because they're supported by massive infrastructure investment.
Massive. Specifically, the reports point to the construction of 5E FLOPS computing centers.
5E FLOPS. Just for context for our listeners, that's exascale computing. We're talking about the kind of machines that are used for, nuclear weapons simulations.
It's that level of power. And it's what allows them to iterate on their driving models weekly, sometimes even daily. They feed these models with a constant stream of data from the incredibly dense, chaotic, urban environments of Chinese cities.
So they have the best training data.
Arguably, yes. And their philosophy is different. They're less focused on the theoretical why of a model's decision and almost entirely focused on the empirical evidence that it works.
Okay, so that's China. Now let's contrast that with North America. The report calls this region the foundation model leader.
And this is the strategy really being led by Tesla and Waymo. It's distinct from China's approach. It focuses on the AI factory concept. Tesla's Dojo project is the prime example.
And the bet here is different.
The bet is that if you have enough raw compute power and a clean enough software architecture, you can build a single generalizable foundation model. A model that understands the concept of driving, not one that just memorizes routes or scenarios.
So it's a more fundamental first principles approach.
Exactly. It's a very high capital, very high compute play. They're trying to solve the general problem of AI applied to driving.
Okay, so we have speed first in China and foundational in North America. And then we have Europe, the regulator.
It sounds defensive, doesn't it? But it's actually a form of strategic differentiation.
How so?
Europe, driven by the EU AI Act, is effectively trying to define the global standard for what trustworthy AI even means. Companies like Volkswagen's Cariad, Bosch, and the whole consulting ecosystem around them, like FEV and AVL, are focusing heavily on building safety frameworks.
So their sales pitch is safety, not features.
Their pitches: we might not be the first to feature complete, but we will be the first to be provably safe. They're not trying to win the speed race. They're trying to build a compliance moat.
A compliance moat. That's a good way to put it. Now, I was surprised to see a fourth major player emerging in the data, the petrocompute pivot.
This is a fascinating and very recent development. You have the Saudi Public Investment Fund, the PIF, pouring billions, I think of $7.5 billion announced at LEE 2025 alone,
An incredible amount of money.
into a strategy of skipping the internal combustion age entirely. They're building new car companies like Sear and entire industrial cities like Oxagon.
So it's a total greenfield strategy.
Exactly. Think about it. They aren't trying to retrofit a 100-year-old factory in Detroit or Wolfsburg. They are building AI-native manufacturing hubs from scratch, using the latest NVIDIA infrastructure as the foundation.
And they're leveraging another region for the actual manufacturing?
Yes, they're using Southeast Asia, specifically Thailand and Vietnam, as the manufacturing arm for these new ventures. It creates a completely new axis of power in the industry that didn't exist 5 years ago.
So the landscape is fragmented, the competition is asymmetric, everyone is running a different race. Which brings us to Section 2, the engineering revolution. This is where the rubber meets the road, or maybe where the code meets the simulation.
This section directly addresses that need for speed flank of the pincer we talked about.
Hmm.
How do you actually physically compress a development cycle from 24 or 36 months down to 12?
You can't just tell the engineers to work harder.
No, you'll break them. You have to change the physics of development itself.
The report we're looking at talks about a major shift from computer-aided engineering, CAE, to AI-augmented engineering, or a CAE. The big headline here is Physics AI.
This is, and I don't think I'm exaggerating, the biggest breakthrough in mechanical and systems engineering in decades.
Why? What was the old way?
Traditionally, we use the V model. You design on the left side of the V, and then you verify and validate on the right side. The verification step things like computational fluid dynamics, CFD for aerodynamics, or finite element analysis, FEA for structures, is the bottleneck.
It's always been the bottleneck.
Always. It can take days, sometimes weeks, to run a single high-fidelity simulation on a supercomputer cluster.
Right, because you're literally solving the Navier-Stokes equations for every single cell in a massive mesh. It's computationally brutal.
It's brutal. Physics AI changes the entire approach. Instead of solving the equations from first principles every single time, you use things like graph neural networks, GNNs, and surrogate models.
Okay, so what does that actually mean?
It means you train an AI on your company's last 10 years of simulation data. You teach it the pattern of how air flows over a particular car body or how fluid moves through a specific pump design. The AI learns the physics from the data.
So it's not calculating the answer. It's predicting the answer based on what it's learned.
It is predicting the outcome of the calculation, yes. And the speed difference is staggering. I mean, it's hard to even comprehend.
The reports have some case studies.
Yes, from SimScale and Schaeffler. They're showing a reduction in simulation time from hours down to seconds. We are talking about sub-second predictions for complex aerodynamic flows.
There was a specific case that stood out to me about RLE International and KSB on pump design.
That's a great example. They took a pump design cycle that used to take 1 full month, and they reduced it to 42 hours.
From a month to less than 2 days.
And in another case, they were predicting full vehicle aerodynamics in 10 seconds. Now, the immediate critique from any good engineer is going to be, but is it accurate?
That was my next question. What's the error rate?
The report shows an error rate of less than 3.4% when compared to the high-fidelity culvert.
Okay, 3.4% is significant if you're doing final validation for safety. You wouldn't launch a car based on that.
No, of course not. And that's the strategic key here. This is so important. You don't use physics AI for the final sign-off.
You use it for exploration.
Exactly. Use it as a base camp. You use the AI to explore 10,000 design variants in a single afternoon, something that was physically impossible before. You let the AI narrow the massive design space down to the best 3 or 4 options.
Then you run the expensive, slow, high-fidelity, traditional solver on just those few promising candidates.
Precisely. It completely flips the workflow from verification to exploration. It unleashes creativity.
And it's not just about simulating existing designs, though. The next step is generation. The reports talk about generative design.
This is the next logical evolution. A great example is AVL's vehicle composer software. The old way, an engineer would draw a chassis in CAD and then test it.
Right.
The new way, the engineer inputs a set of constraints.
What kind of constraints?
Things like, I need 500 kilometers of range, the battery pack must weigh no more than 400 kilos, it has to have a 5-star crash rating, and my total cost target is X.
And the AI designs the car.
The AI generates the optimal 3D layout, it places the structural members, it routes the cooling loops, it specifies the battery size and shape, all in minutes.
So the engineer's role shifts. They become an architect of constraints rather than a drafter of parts.
A perfect way to put it. And we're seeing the exact same shift happening in software development with something called agentic AI.
Let's differentiate agentic AI from just using a simple coding assistant like, say, GitHub Copilot.
It's a huge difference. A coding assistant completes a line of code for you. An autonomous agent completes a task for you.
Give me an example.
Okay, companies like HCL Tech and ASAP are deploying agents that don't just write code. They perform the entire requirements analysis, they design the software architecture, and this is crucial, they do the testing.
The report mentioned a specific kind of testing. White box fuzzing. What is that?
This is critical for cybersecurity. Fuzzing is basically just throwing millions of pieces of random data at a system to see if you can break it.
Right.
White box means the agent isn't just throwing random data, it has access to the source code. It analyzes the code's structure and intelligently generates the poison data specifically designed to target potential memory vulnerabilities.
So it's looking for the weakest points and attacking them directly.
Yes, it finds bugs that human code reviewers almost always miss because humans are not good at imagining millions of bizarre edge cases in memory allocation. The agent does this autonomously. 247.
Okay, so we're building the car faster, we're coding the software for it faster. That brings us to section 3, product architecture. What is it that we're actually building with all this new speed? The big headline is end-to-end autonomous driving.
This is maybe the biggest, most controversial shift in the entire industry. It's the move away from modular pipelines and towards photon-to-control.
And this is a religious war in the ADS and autonomous driving community right now.
It really is. The traditional camp, the incumbent camp, believes in modularity. You have separate boxes for each step.
You have perception, which asks, what do I see? Then prediction, where is that thing going?
Then planning, what should I do about it? And finally, control, which is steer, brake, accelerate. It's a chain of logic. It's explainable. You can debug each module separately.
But it's brittle.
It's incredibly brittle because information and context are lost at every single handoff. You see a complex situation and your perception module labels it pedestrian.
And in doing that, you lose the nuance.
You lose the nuance that the pedestrian is looking down at their phone and they're stumbling towards the curb. That context is gone.
So end-to-end, it removes the modules.
It collapses them into one. Raw sensor data, literally the photons hitting the camera sensor, goes into one massive neural network, and steering and braking commands come out the other end.
Tesla's FSD version 12 is the prime example of this.
It's the poster child.
Yeah.
They famously removed 300,000 lines of explicit C++ code, all the hard-coded rules like, if you see a stop sign, then stop. And they replaced it all with a single neural net trained on millions of hours of human driving video.
So the system is now driving based on intuition, not rules.
Intuition is exactly the right word. It learns the feel of driving in a way that a rules-based system never could. But this creates a huge philosophical and engineering problem.
Which is, how does it handle things it has never seen before? The dreaded long tail problem.
The person in the dinosaur costume crossing the road.
Right. Or a weirdly shaped box that fell off a truck.
Yeah.
The old system might fail because it can't classify it. How does the new system handle it?
This is where the perception architecture itself is evolving. Huawei's ADS 3.0, for example, uses something they call a Godin network, general obstacle detection. It relies on a technique called voxelization.
Okay, break that down for me. Voxelization.
Think of the world around the car as a 3D grid made up of tiny cubes called voxels, almost like the world is made of Minecraft blocks.
Oh.
The AI's job is no longer to classify an object. It doesn't need to know that is a dinosaur or that is a weird box. It just needs to determine one thing. Is that voxel occupied by solid matter or is it empty space?
So it simplifies the problem from the impossible, what is that, to the much simpler, is there space to drive through?
Precisely. If a voxel is occupied, the cost of driving through it is infinite. Don't do it. It completely solves the classification failure mode. It's a much more robust way of seeing the world.
That's perception. What of the planning part? How does it decide what to do?
This is where we're seeing the rise of world models. This leverages the same kind of generative AI that we see in things like Sora or Midjourney. Technologies like NeurFF neural radiance fields and 3D Gaussian splatting.
This sounded like pure science fiction when I was reading the reports. The car, it hallucinates.
A better word is simulates. The car is constantly asking itself, what happens if I accelerate into that gap right now?
And the world model answers that question.
The world model generates a short video, a predictive hallucination, if you will, of the next 5 seconds of reality based on that action. If that generated video depicts a crash or a near miss, the car discards that plan and tries another one. What if I brake slightly?
It's essentially imagining thousands of possible futures every second to select the safest path forward.
That's exactly what it's doing.
But to run a real-time video generation model inside a moving vehicle, the compute and data bandwidth requirements must be astronomical.
Which is why the underlying physical architecture of the car has to change.
Yeah.
This is the enabler. We are moving to a zonal architecture. You can't have a traditional wiring harness that weighs 80 kilos running a dedicated wire from every single sensor back to a central computer. It's too slow, too heavy, too complex.
So you consolidate.
You consolidate. You have zonal controllers, front left, front right, rear, that collect all the sensor data in that zone. Then they packetize it and ship it over a high-speed gigabit Ethernet backbone to a central compute brain.
And that central brain isn't just focused on driving the car, it's also watching the driver. The reports call this the empathetic smart cockpit.
Yes, and this is another huge shift. We're moving from a command-response interface, hey car, turn up a heat, to contextual understanding.
LG and Renesas are pushing this hard.
They are, and it's a hybrid AI approach.
Meaning it uses both the cloud and the onboard computer, the edge.
Yes. You have small language models, or SLMs, running on the chip inside the car for immediate private tasks. Things like adjusting the seats or simple queries that don't need an internet connection.
And then for more complex things.
For complex reasoning, it queries a large language model, an LLM, in the cloud. But the real key is the sensor fusion. It's not just listening to your words.
What else is it sensing?
It's using interior cameras to track your gaze and your posture. It's using microphones to analyze the tone and stress in your voice. And this is the newest part, it's using radar to monitor your vital signs.
Radar for vital signs. How does that work?
It's a technique called RPPG, or remote photoplethysmography. The radar can detect the micro vibrations of your chest wall as you breathe and as your heart beats. It can get an accurate reading of your heart rate and respiration rate without touching you.
That's incredible.
It means the car knows if you are stressed or angry or getting drowsy, even if you don't say a word. And it can adjust its own behavior, maybe increase the ADS sensitivity or suggest you take a break accordingly.
That is deeply impressive, but also slightly dystopian. Which brings us, I think, to the most critical section for all the engineers listening to this. Section 4, the safety and compliance modes.
It's the compliance wall. This is where it all comes together.
So, if we are moving to these end-to-end neural nets that drive based on a learned intuition, and they plan by hallucinating possible futures, how on earth do we prove that they are safe?
That's the billion-dollar question.
Because the old standard, ISO 26262, it was all about predictable failures. It's about hardware failure rates. A capacitor blows, a resistor fails.
Right. ISO 26262 assumes that the system was designed correctly in the first place, and your job is to protect against random hardware failures over the vehicle's lifetime. It has absolutely no framework for dealing with AI. It cannot handle what is known as functional insufficiency.
Let's define that term very clearly.
Functional insufficiency is when the hardware works perfectly, the code executes perfectly, every transistor does its job, but the AI still makes a catastrophic decision because it fundamentally misunderstood the environment.
It wasn't a failure in the traditional sense.
No. The function it performed was just insufficient for the complexity of the task. It did what it was trained to do, and what it was trained to do was wrong in that one specific novel moment.
So we need a new standard, a new way of thinking about safety.
And we have it. ISOPUS 8800. It was officially released in late 2024. And the reports we're looking at were not wrong to call it the new Bible for AI safety in road vehicles.
So what are the core pillars of 8800? How does it change things?
It's designed to bridge the gap between the hardware-focused world of ISO 26262 and the probabilistic reality of AI.
Okay.
The first major pillar is the data lifecycle. You'll find this in clauses 9 through 11. It mandates, for the first time, that your training data must be treated with the same rigor as your source code.
Data is source code.
That's the mantra. You must have rigorous specifications for how that data is collected, how it's cleaned, how it's labeled, and how it's augmented. If you cannot trace the complete lineage of your training data, you cannot certify the car, period.
And the second big concept, which seems to be the entire industry's answer to the black box problem, is the safety envelope.
It is the only viable answer right now. The safety envelope is a simple, deterministic, rule-based monitoring system that sits outside the complex AI. It is the AI's chaperone.
So the complex end-to-end AI has full control of the car, unless
it tries to violate a fundamental law of physics or a non-negotiable safety rule. For example, the intuitive AI might decide to accelerate because its training data suggests the gap in traffic is open.
But the safety envelope is also watching.
The safety envelope, using a simple, reliable radar sensor and basic physics equations, is constantly calculating the time to collision with the car ahead. If that calculation drops below a hard safety threshold, say 1.5 seconds, the safety envelope kills the AI's acceleration command and applies the emergency brake.
It has veto power.
It has absolute veto power. So in essence, we don't have to fully trust the black box AI. We just have to trust the simple, explainable cage we put it in.
We trust the AI to optimize for comfort, for efficiency, for a smooth ride. But we trust the envelope to optimize for survival.
That's the model. And it's not just standards. We also have the EU AI Act. This isn't a voluntary best practice. This is binding legislation.
And it has teeth.
It has very sharp teeth. And it explicitly classifies automotive AI as a high-risk application. This imposes strict, legally binding requirements on transparency, human oversight, and documentation.
You have to be able to explain your system to a regulator.
And you need to generate these massive conformity assessment reports, which, again, brings us back to tooling.
Because you can't do that manually.
Yeah.
It's impossible.
No engineer could possibly generate that much documentation. So you see companies like Electrobit building these compliance frameworks that automate the process. Your AI development pipeline has to effectively write its own legal defense as it goes.
Okay, that is a massive amount to take in. We've covered the strategic landscape, the engineering tech, the product architecture, and the new rules. Now, let's wrap this all up with Section 5, Implementation Strategy. We promised a consultant's playbook. If I'm a CTO listening to this, what do I do on Monday morning?
The synthesis of all these reports really points to 4 clear, specific, strategic recommendations.
Okay, let's hear them. Recommendation number 1.
Implement the hybrid simulation workflow. And this is a message of evolution, not revolution. Do not discard your high-fidelity solvers. Do not fire your CFD team.
They're still essential.
They are essential, but for the final step, you must relegate high-fidelity simulation to the validation phase. You must adopt physics AI tools, like the ones from SimScale, as your Basecamp tool for rapid, wide-ranging design exploration. Shift the bulk of your engineering iteration cycles to the surrogate models.
Explore with AI, validate with physics.
Perfect summary. Okay, recommendation 2.
Go ahead.
You must treat data governance as a core competency. The old adage, garbage in, garbage out, is no longer just a saying. It is the single biggest threat to passing an ISOPUS 8800 audit.
So you need a central authority for data.
You need what some reports are calling a data governance hub. It's a concept that a company like Upstream Security advocates for. You must break the silos between your manufacturing data, your field data from the fleet, and your R&D simulation data. It all has to live in one governed place.
And this means the data coming from the car that's actually on the road needs to feed directly and cleanly back into the training loop, but with context.
That's the critical word, context. Using digital twins that are enriched with context, not just raw canned bus logs, you need to know why the driver took over. Not just that they took over. Was the sun in their eyes? Was the road marking confusing? That context is gold.
Okay, recommendation number 3.
Embrace agentic AI for the software development lifecycle, SDLC. And I mean, really embrace it. Move beyond simple chatbots and coding assistants.
Deploy the autonomous agents we talked about.
Yes. Deploy autonomous agents for the tedious, high-volume, error-prone tasks, generating ISO-compliant documentation from requirements, running fuzz tests, 247, and managing requirements tracing. But, and this is a critical constraint for engineers, you must use hardware-aware static analysis.
Why is the hardware awareness so important for these AI agents?
Because a pure software AI agent doesn't instinctively understand the brutal constraints of an embedded automotive chip. It might write code that is logically perfect and beautiful, but it completely blows your memory budget or your CPU cycle limit.
So the agent has to know it's writing code for a $10 chip, not a cloud server.
The agent must be constrained by the specific real-world hardware limitations of the target ECU. Otherwise, its output is useless.
Okay, that makes sense. And the final recommendation, before.
Immediate adoption of ISOPUS 8800.
Don't wait.
Do not wait for the regulators to force you. Do not wait for the deadline. Start today. Start mapping your current AI failure modes to the new ISO 8800 framework now. Treat compliance not as a burden, but as a competitive advantage.
How is it an advantage?
Because if you are the first OEM in your class to be verifiably 8800 compliant, you have a massive, massive advantage for entering and succeeding in the European market. You've already built the safety moat.
So if we synthesize all of this entire transition from 2024 to 2026, it's really about moving from experimental AI to industrial AI.
That is the headline. We are industrializing the magic. We're taking these incredible, almost magical capabilities and putting them into a rigorous, safe, repeatable industrial process.
And in doing so, it completely changes the definition of what an automotive engineer even is.
It does. For a century, an engineer designed parts. Now, they're no longer just designing parts. They're becoming AI trainers and safety guardians.
What does that mean in practice?
It means they define the constraints for the generative design tools, they curate the data that the driving models learn from, and they design and validate the safety envelope that the AI operates within. The AI does the brute force work, the human provides the wisdom and the oversight.
Okay, I want to leave our listeners with a final provocative thought to chew on. We've talked today about end-to-end AI that drives on something like human intuition. We've talked about generative AI that designs the physical parts of the car.
So here is the thought to take with you.
This new world, we are on the cusp of building systems that are statistically provably safer than human drivers. They won't get tired, they won't get distracted, they won't drive drunk. They will likely save thousands of lives every year.
The data points in that direction.
Because they are black boxes, and because they rely on this probabilistic intuition learned from data, are we as a society and are you as an engineer prepared for a reality where we can't fully explain why the car did what it did?
We can explain the safety envelope, we can point to the rule that fired, we can explain the physics. But the core intuition of the neural network, that might remain fundamentally opaque. The grand trade-off of the AI era might be accepting a degree of opacity in exchange for a higher degree of safety.
A difficult question. So the final word from this report is, don't wait for the regulations to force your hand.
Build the safety envelope now. It's your only path forward.